changed my password, so I got kicked off. Okay, so I'm recording, and then following up on the question you just asked, Kevin, I'm actually fine with you just keeping it in terms of information of Lambda. Like you don't have to plug in the Lambda hat for this particular one because in the question itself, it's not saying I of Lambda hat that it's asking for.
I had another follow-up.
Sure.
Don't we know the expectation of the sum of yi equals n lambda? So we can substitute that in?
Well, essentially, yes, but I was sort of kind of not explicitly stating that.
Oh, sorry.
So
we'd have to calculate it either way for the walled confidence interval, right?
Mm-hmm. You mean you have to calculate I of lambda hat? Yeah.
Yeah.
But you can just plug that into the lambda, to the I of lambda that you got in the previous step, the information that you got there. Okay.
Or what is that, the information?
Any other questions?
Yes, I have a question. I don't understand 3A at all. I don't even know where to start.
So
For the delta method,
so let's so I can walk you through this, but what do you, so maybe it'd be helpful though just to give me some tips on where you're confused.
so I know that for the delta method, you need to find so we start with the what is it? So we start with the function and we need to find the estimator, something like that. I don't know. I'm not sure actually.
So for you can actually, this looks a lot more similar than the previous problem than you may realize. So I want to here, I'll get started by just writing down the problem here. So 3A gives you, I'm just going to write it as S tilde because I can't really write this squiggly thing. It's just, I never have been able to. It's called Kasi, the Greek letter, but I'm just going to write S tilde instead. And that's, we're defining that estimator this way, which is just the proportion of zeros in the sample. And I'm asking you to find the variance, but so we let's look at this piece first. This is an indicator, right? So does this look familiar from what you saw in the previous problem or stuff that we've talked about before?
Yes.
So let's say I define a variable z equals indicator of yi equals 0. Do we know what distribution z takes?
Bernoulli.
Yeah. And can we figure out, I just spelled Bernoulli wrong, but can we figure out what the p parameter of that Bernoulli distribution is going to be in terms of the parameters of y? So the other piece of this problem we have, so we know that y follows a Poisson distribution. And we're also given that the probability of y1 equals 0 is e to the negative lambda, which you can calculate from that Poisson distribution. So essentially, that Bernoulli parameter is going to be the probability of y I equals 0. So what's that going to be? So all of the y's are identically distributed and independent. So what that means essentially that y1 and y2 and y3, they all have the same distribution. So
Will
the
it be the exponential negative lambda?
Yeah, so the probability that yi is equal to 0 is the same as the probability that y1 is equal to 0 because they're identically distributed, which we know from, because we're given in the problem, is equal to e to the negative lambda. Does that make sense?
Yes.
Okay, and then so going back to our original estimator up here that we defined as part of the problem that we want to get the variance of, now we can rewrite that in terms of z. So now it's a sum of this zi variable. Does that make sense?
Yes.
And so what is the variance? What is the expectation of zi? And what is the variance of zi?
Isn't the expectation zi equals 0? Or is that wrong?
Why?
I
So,
don't know. I get really confused with this.
so what do we know about zi? That we just talked through, that we just talked about. How did we just define it?
Like a Bernoulli?
We said zi is a Bernoulli variable, so we know zi's distribution. And what are the expectation and variance of a Bernoulli variable?
E?
P is the expectation and P times 1 is P. That's the variance.
Yeah, exactly. And so we also know what P is in terms of lambda, because we defined that right here. So then what is our expectation of zi in terms of lambda and our variance of zi in terms of lambda?
So for the expectation, be exponential negative lambda?
Yeah, so that will be e to the negative lambda. Which is also just the probability that yi is equal to 0. That's going back to our original definition. So yeah, this is going to be your expectation of zi in terms of lambda. And what about the variance?
E to the negative lambda times 1 minus e to the negative lambda?
Yes, exactly. Okay, does anybody have questions about this so far?
No, this is extremely helpful going through this. Now this makes sense.
And so now we have all of the pieces we need to answer this part of the problem. And it's really, so now we go back up to the original definition of the estimator, which I rewrote here in terms of ZI, because I think it's just nicer since we have the pieces we need, the expectation and variance of ZI, and we want the variance of this estimator. So we want the variance of S tilde. And so the first thing I would do is just plug in what's on the right-hand side of this equation. And you can simplify this quite a bit. And some of this is just being familiar with operations that you can do with the variance. So I'll write some of those in the corner here. But does anybody know how I can simplify this further? Just from where I have it right here. Like what can I do at the end? Can I pull out the n? So typically we only take variances and expectations of random variables, right? So if you let X be some random variable, we don't have to know the distribution. Sorry, my iPad just shut itself off for a second. Okay. So what is going on? Sorry. Okay, so the variance of some constant c times x is just going to be c squared times the variance of x. That's just property of variance. So then you can pull out this n term using that property. Okay, and then what about the summation that we have within the variance? What can we do with that? Can we pull it out? Yes or no? Is there a reason why? If we can.
Wouldn't that be n times variance of ZI? Something like that?
So you're saying if we're gonna say n times variance of ZI, you're implicitly pulling the summation sign out and then converting that to an n. So I don't want to like step ahead quite away. So, but you're saying, well, yes, we can pull it out, right? Essentially. I'm basically asking, like, can you take this summation and pull it out of the variance operator? And under what conditions can you do that? So there's another rule of variances that I'm going to write over here. So the variance, if you have two random variables, x and y, the variance of x plus y is equal to the variance of x. I'm running out of space, I apologize, plus the variance of y minus 2 times the covariance of x and y. However, what's the covariance? If you assume that x and y are independent, then what's the covariance of x and y?
At 0.
Yeah. So in this particular case, the y's are independent, which means that the z's are going to be independent. And if the z's are independent, then we can pull this summation term out. Because this covariance that would have to exist between all of these separate ZI terms within is going to be equal to 0. But that you can only pull out that summation when the random variable, you can only pull out the summation of from the variance when the random variable is independent, when they're IID. And so I know like you probably have to recite in other classes if you're assuming that variables are IID, and this is one of the reasons why a lot of the calculations that we do really only hold when the variables are independent, and you have a much more complicated set of calculations if they're not. So that's what's going on there. And then I can do what you said, Lola, and okay, I have a summation now outside of the variance. I can say that's equal to n over n squared times the variance of zi equals 1 over n times the variance of zi. And what's the variance of zi?
Isn't it that exponential times 1 minus the exponential to the negative power?
Yeah, so we calculated that up here, so we can just plug it in. Does that make sense?
Julia, do you mind just
And
scrolling down a
then-
little bit on the whiteboard because it's cutting off for some reason on our view? Awesome, thank you.
So if I understand, we don't really need the delta method here to find the approximate variance. We just need to do some transformation, stuff like that.
Right, you need the delta method in part B though.
So then in part B, where does n come into it?
Where does n come into it?
Yeah, in the delta method.
Yeah, so I'm gonna sort of rewrite the delta method out here in a form that I like better than the slides, and I think we'll change them for next year. So I'm still like iterating the slides from the content that I originally received, since this is my second time teaching the class, and I'm always happy for feedback about versions that you find to be less or more helpful. But so the statement of the delta method, say you have some random variable or some estimator theta hat, and you know that theta hat follows has an asymptotically normal distribution, and so I'm writing out the math for that here. So that means as your sample size goes to infinity, your distribution is asymptotically normal. And you know the mean and the variance. And so all estimators from the exponential family that are MLEs have an asymptotically normal distribution that takes this form. And you know what the asymptotic variance is going to be because it's the inverse expectation, or sorry, the inverse information right here. I have sigma squared written in the notes, but sigma squared is sort of a stand-in for the more general way of expressing that, which is the inverse information. So then what the delta method says, if you have some transformation of your estimator theta, I called it tau of theta hat. So some function that you're applying to that, you can also find the variance of the asymptotic variance of that estimator. And what the statement of that looks like is then that transformation of your original estimator still has an asymptotically normal distribution. and you can find what its variance is. Using this property of the delta method right here. So you just take the derivative of that function, that transformation of your estimator, and then you multiply it. Then you square it and you multiply it by the inverse information. I may have gone off on a tangent there, but does that make sense? Do you have any other questions related to that?
Not yet. I just have to work through it a little bit. Thank you.
Can you walk through like 2C? Through the information about lambda based on this sample.
Oh yeah, so this one is kind of just a little bit ugly.
That's what I was wondering because mine looked stupid.
No, it's just kind of ugly. I actually, I can go through the start of it, but I encourage you guys to work through this one on your own. I'm not going to go through all of it.
Could you just start it so I can see if I have something similar?
Yeah, sure. So where are we starting here? It's the information of lambda based on this sample and hence the variance. So I have to back up a little bit.
So I think I had plugged in, I had used the log likelihood function where I plugged in the pi in terms of lambda to find the MLE, and I think I had like log sum of x over n minus 1.
So we have y is distributed Poisson with the lambda parameter, and we have y star, which we define as an indicator of yi being greater than 0, right?
Mhm.
And then you can show that yi star as a binomial Bernoulli distribution, with p is sort of the generic parameter for that, and you know that p is equal to some function of lambda, right? And you show what that function is.
Mhm.
And then so in B you write that, and so then you write down the likelihood based on this lambda, which is going to be a Bernoulli likelihood where you plug in this here. Makes right?
Yes.
And then so then you take the you derive the information so I guess you really have to write out the whole likelihood in order to do that. So the log likelihood, the likelihood is going to be, hold on, I'm just going to erase that. I'm hesitant to walk through all of it and give all the answers exactly because I want you guys to work through it a little bit on your own as well. And also, I think it can be valuable to do that, but I do want to make sure that the concepts make sense. And it sounds like you're on the right track. So what do you have for your likelihood?
The function or the MLE?
So you don't need the MLE in order to calculate the information.
Oh, okay. So the likelihood.
You will for the information based on the sample, but I'm saying, yeah, start with the likelihood.
Yeah. So the log likelihood function, I think I had sum of x log 1 minus e to the negative lambda plus lambda sum of x minus lambda n.
Is X like the new variable?
Yeah, where I defined x as being 0 if y was 0 and everything else was greater than 1 or equal to.
So can you repeat what you had for that likelihood for me?
The sum of x times log 1 minus e to the negative lambda plus lambda times the sum of x minus lambda times n.
Oh, can you, sorry.
Oh,
slow down a
sorry, oh yeah, log 1 minus e to the negative lambda.
So some of,
So sum of x, yeah, times the log of 1 minus e to the negative lambda
okay,
plus, and then I had like the sum in parentheses 1 minus x, so I took that out as the sum of x minus n.
the sum of, in parentheses, oh yeah, sum of xi minus n, that's what you have?
Yeah, times lambda.
Got it. Okay, so,
Or actually, it's the sum of 1 minus x times negative lambda. So yeah, that should be right. Sorry, that's it.
times negative lambda?
No, I think that is what I have right there.
Okay, and so I'm not confirming like or denying if this is right. I think I'll leave that to you guys to sort of double check on this. But so going from here, first you calculate the score. And actually I'm gonna rewrite this so that I have the x's on the right hand side just because, and the functions of lambda on the left hand side, because I just like it that way. For if I'm about to take the derivative. So then, right, you'll take the derivative with respect to lambda of this log likelihood, which gives you the score, right? And then you take the derivative again to get the information. And so,
and I think I ended up with like a lot of like sums in my variance, and I'm a little bit like confused about when things can be simplified and when they can't as well.
what do you mean by sums in your variance?
Like sum of x.
So I guess I'm not sure without specifics, like how to answer the question. I'll go ahead and take the score here and see if I can put it into a form that's a little bit nicer, but yeah, I don't know. I don't want to give too much away. So first you have to take, yeah, I don't know. I'm sorry.
Yeah, no, I understand. And I am just wondering if
This is
there's,
kind
a
of
form
like,
that's
this one's
a
kind
little
of
bit
just like,
nicer.
it's a little bit messy. It's kind of just using the chain rule to take those derivatives and making sure that you're checking your work as you go. And kind of the purpose of it is to show that if you use some of these other properties, like the invariance property, that it's like a lot easier to find these sorts of
Okay,
things.
that makes sense.
Any other questions?
I have one question. How do we submit our like homework corrections for the clawback points?
Yeah, that's a good question. You can submit them. I guess there needs to be like a place for that open on CourseWorks, doesn't there? I'll set something up after office hours today. There's no deadline for you submitting those. You can kind of do them at leisure, but I have to put up an example of what I want you to do. And I guess I need to have some place for you to submit it. So yeah, I'll get something figured out for that.
Cool, thanks. No rush for me anyway. And I guess if there's no other questions, could you go through a quick example of the delta method?
Yeah, sure. So I'm gonna do something. I'm gonna try to come up with a sample, an example that's similar to homework, but not exactly the same. And I'm gonna go back to that statement, or is right here that I have written out. I'm gonna erase some of this stuff here so we can just. Keep looking at this part. Okay, so let's still assume that that our y's have a Poisson distribution. And let's also assume that our tau of lambda that we're interested in is, I don't know, you guys can make something up. Let's say lambda cubed. 3 times lambda cubed. That's our transformation. And so we can use the delta method to find the variance of this estimator here. And so I'll show an example of that. But first, what we need to do is figure out what the asymptotic variance of the original estimator lambda. So lambda hat is going to be the MLE. So I guess one step I sort of glossed over, and let's assume that lambda hat is the MLE of lambda when y has a Poisson distribution. So what is that equal to? You've calculated that now. So like, what's that going to look like in the generic form? The MLE of the Poisson parameter.
Is this like from 1A?
Yeah.
Or B, I mean, yeah, it's like the sum of yi over n, or the mean.
Yeah, so that's just like y bar, the mean, same as the MLE for a normal distribution. And then following this piece up here, so that we can use the information which you also calculated to get the variance. And you give me that as well.
For information, I got n over lambda.
N over lambda, that seems right to me. And so then your inverse information is going to be lambda over n. Okay. So that's one piece. That's like this piece here. So we can calculate this other piece. And so what is the derivative going to be of our transformation of the MLE?
9 lambda to the fourth. Or, I mean, to the second.
Yeah, there you go. Okay, so we have that piece. And then we can just square it. Cool. So now we have everything we need. And so the estimated variance of our transformation of the MLE is just comes from putting those pieces together. Makes sense?
Cool. Yep. Thank you.
And I'm fine with you just leaving it in this form for the homework. You don't have to plug in like whatever lambda hat is equal to.
I have a small question about homework 1, if that's all right.
Sure.
So I got some points off for not specifically stating the canonic link, but I kind of thought I was doing that by just writing t of y equals y. But what should I have done instead?
So the canonical link was going to be, so once you have your distribution, I don't know what your homework looks like specifically because the TAs created the homework, but once you have your distribution in exponential family form, and I gave back a lot of points on the homework because I think I wasn't explicit about what I was looking for, but in this case, I think I did ask for the canonical link, but but no, it's a good question. So when you put it in the exponential family form, you end up with your t of y times theta minus b of theta over a of phi minus or plus some function of y and phi. That's the form for the natural exponential family. Sorry, it's so messy. Yeah, and then you have your t of if t of y equals y, then it's in canonical form and you're in the natural exponential family. But the canonical link, so theta is going to be equal to something here, right? And it's going to be like, say your original parameter is lambda, theta is going to be some function of g of your lambda, some function of the original parameter. And this is the canonical link. Is the function of your original parameter defined by theta when your distribution is in natural exponential family form.
Okay.
We can, if you're, I'm happy to talk to you about it, sort of through email or outside of class time. I just
No, that's fine. That's fine. I was just wondering, like, because I thought I was doing it, but that makes sense. So no, that's okay. Thank you.
Yeah, no, I get it. I think that this is something. So it's really just like a definition of a like specific subset of the exponential family. And that gives it certain properties. But it's not, there's no like intuitive explanation for it. It's just kind of like one of those things you have to just kind of accept.
Sure. No, that's totally fine. I was just wondering what I should have done. So thank you.
Yeah, no problem.
I have another conceptual question. Just for a quick review of, are the assumptions for the different hypothesis tests all the same?
I am going to look at my notes before I answer that fully. But so certainly, like you have identically independently distributed random variables is like the most important underlying assumption.
And then sufficiently large sample size,
Yeah,
because we're all asymptotic tests, correct?
yeah, so that's actually that's I would say that they are the same. And those are really the major two.
Yeah, just want to make sure I wasn't missing something.
Yeah. Yeah, I mean, once you are in a regression setting, then you like would have an additional assumption, like say you're doing logistic regression, then you're assuming that the X times betas have a linear relationship with the logit of your probability of observing like Y equals 1. So that's like an additional assumption that you put on when you have a regression model. So like with Poisson regression, you use a log link. So you would have like an assumption of a log relationship with the X times betas. Basically a linear relationship with the transformation of the outcome. But
I remember that from the lectures, the linearity assumption. Okay.
But yeah, no, it's just IID and large sample size for the general setting.
Great.
Thanks for all your great questions, guys. No.
Are you able to walk through another example of the score test?
Yeah,
I know we
sure.
can't do them for the homework, but I just keep not getting the parameters to plug in, so something must be wrong.
Yes. Hold on. I think I need to reshare here.
Oh, no.
What do you mean that you keep not getting parent parameters to plug in? Can you...
Well, because ideally we want to get the values we were given, right? So that we can plug them in and get an actual value for the score test or values.
Oh, so you mean you can't use the sufficient statistics that were
Yeah, like the
provided
sample
for...
needs that we were given. Yeah.
Yes. So would it be helpful to go through the example from lab the other day again in like a little bit more detail?
Sure.
Okay, so I'm gonna start there. And I have to just pull that up. Yeah, because you should be able to use the things that the information that you have. And you should be able to plug that in, and knowing that like if you have like a sum of y, we have like 1 over n, sum of yi equals 1.3. So if you have a sum of yi without the n, then you can just say like n times 1.3. But I'm assuming that's not what the issue is for you.
No.
Yeah, okay.
Um.
I didn't think so, but doesn't hurt to check. So I don't remember the lab example that I made off the top of my head, so I have to pull that up real quick.
Okay.
And I can like edit it a little bit, but it's usually easier to start from something. Okay, yeah, so let's say, I mean, we can even pick a new distribution and just do it that way. But I don't know if I'm gonna have the sufficient statistics I need. So I'm just gonna start from the example from lecture, sorry. Just give me a minute.
No worries.
Oh, did I put up the correct annotated lecture notes yesterday? It looks like I have 2 copies floating around in my folders, and one's wrong and one's right. Okay,
Should
so,
be.
sorry, go ahead.
I was just saying there should be one somewhere. I was looking at it the other day.
Yeah, I did like a similar lab last year, but I changed some things around. So hopefully it's the stuff that we went over yesterday, but it sounds like it's okay. So I'm going to start with the score statistic, like the generic form of it. Okay, and then in the homework problem that I went over, the problem I went over in lecture, I say, okay, you're given some information that I'm going to put over here on the side. You're given that the sum over I of log yi is equal to 18.3, and that n is equal to 100. That I simulated this from theta equals 5. So actually we have theta, we don't have lambda here as our parameter. Okay. And then the null hypothesis, I'll just put a different null hypothesis in. Let's say that we want to test the hypothesis that theta equals 6 versus theta is not equal to 6. And we calculated as part of that, we have the distribution of the data, which is Pareto, which looks like this. Using that, we calculated a couple things. We calculated the score. And we calculated the information. And then so the generic form of that test statistic is going to be n over theta minus sum over I of log yi squared over n over theta squared. And you can plug in the value of theta at the null hypothesis for the score test. So in this case, and you can also plug in the value for n, so you get 100 over 6 minus and 18.3 squared. Though I'm guessing that maybe it would be helpful for us to talk through some of where you might be having difficulties, because you're saying you're just not getting the sufficient, you're not getting it in a form where you.
I think I might have like gotten one of either my score function or something wrong. So that might be the trouble I'm having.
Yeah, I would just do exactly what I'm doing here, like write out all the pieces, write out your score function, not in terms of the actual like estimator MLE, but just in terms of like the parameter lambda in this case, and just write out your information in the same way. And then just like sort of write out your generic form of the test statistic, plug in the value for lambda under the null hypothesis, and see if that helps.
Okay.
But we also, if you can, if you're comfortable sort of sharing where you think you may be going wrong, we can talk through that.
Yeah, I think I might have just figured it out. So the information is the inverse of the second derivative, correct?
No, so the information is the second derivative of the log length.
Is the second derivative. Okay.
Yeah.
I think I'm confused about what to do with the ends when you're taking a second derivative. I think that's what I'm getting wrong.
So
and I can give you my specific formula, but I don't know if we can do that.
So like if you have, like, say you have like, I don't know, I'm just making something up, like n times like lambda cubed plus y lambda n, or just y lambda, whatever. So anytime you have, when you're taking the derivative, you specify what parameter you're taking the derivative with respect to. And so that anything that's not that variable is going to be considered a constant. So it's really like a lot of the time we were just working with single parameters, but a lot of the time in reality, you would have multiple parameters, and then you're actually taking partial derivatives just with respect to one variable at a time. So that's an aside, but it sort of implicitly comes up in the regression setting, but we're not going to get into the partial derivative stuff. But anyway, so let's say we have this expression here. I'm just going to rewrite it because I think my handwriting is a little bit hard to read in this case. So we're interested in taking the derivative with respect to lambda of n times lambda cubed plus y times lambda. So anything that is not lambda is going to be treated as constant. Actually, for the hell of it, let's just throw in another n. So we have n times lambda plus y times lambda plus n. So what's the derivative of this going to be? So derivative can be this. I think that what you're probably lost on here is you probably just need a little refresher on the rules of differentiation, and that's totally okay. I'm just going to give myself a little more space. Whatever I said, lambda squared or lambda cubed. And so you can distribute the derivative to each of the terms. So solving this, you have the derivative of that first term plus the derivative of that second term plus the derivative of that third term. So what's the derivative of this first term? Well, n is a constant. Any constant is just sort of going to get pulled out. So if you have the derivative with respect to x of 2x, that's going to be equal to 2 times the derivative with respect to x of x. So that's equal to 2. And this is the same thing. So you'll have n times the derivative with respect to lambda of lambda cubed. Does that make sense?
Yeah.
And then, so this one, same here, y is sort of treated as a constant because that's not what we're taking the derivative with respect to. So you end up with y. And then this piece doesn't have lambda in it. And the derivative of a constant that's not multiplied by a function of lambda, 0, right?
Yeah.
So as a rule, the ends or really any other thing that you come across is just going to be treated as a constant when you're taking the derivative. So if you take the second derivative, you just do the same thing. So the second derivative is just taking the derivative again of this expression that we just came up with.
So it should just be 6n lambda.
Yes. Does that make sense?
Yeah.
Does that help with what you're getting stuck on before?
I need to figure out where I went wrong because I think it might have been before that. But I just need to go through it again.
Hey, Julia. It's Julie. I was wondering for the likelihood ratio test and the walled test, can we use the p chi-square function in R every time for the p-value?
Mm-hmm. So the test statistic is going to be different. But they all have an asymptotic chi-square distribution. So you can use that same function, just plugging in a different value for the test statistic to calculate your p-value.
Okay, perfect.
Hey, Julia, I just have a kind of high level question about, I'm just going through number 2, and specifically with 2D, and I'm really struggling with understanding the invariance property of MLEs. And so, like, I guess I just don't truly understand like the application of that. And I don't know if you can explain that further or kind of define that more definitively versus like what I've gone through with the lecture PowerPoints.
I can try. Though this might be one of those things that has an unsatisfying answer. So I apologize ahead of time if that's the case.
That's
So,
okay.
essentially, I think you're probably looking for more of a why that's true.
Yeah.
And that is the answer to the why is going to be a bunch of statistical theory that I don't remember off the top of my head.
Okay.
Yeah. So really what it more is like a practical result that applies to MLEs that can make it easier to understand potential expectations for new transformations of those MLEs. And like this might seem like some like theoretical thing that you shouldn't care about or that you don't care about in practice, but we actually see things all the time where we have like a continuous version of a variable. Like we might have like BMI is a good example of
Okay.
Of like a variable that is continuous that then we convert to categorical or binary.
Okay.
And so if we know the distribution of the continuous variable and then we transform that variable, then we can also get the, and we know like an estimator for that. We can also like, so that's like the motivation for why we care about transformations of MLEs also being MLEs.
Yeah. Right.
We often transform our variables. And if we know something about the original variable, we want to know what information we can sort of carry forward to the transformation of that variable.
Okay.
So that's sort of the motivation behind it. It is, other than that though, it's just kind of like, at least for this class, a statement of something that you can like accept as fact. Yeah.
And this would be like a really stupid follow-up question to that. So is this the invariance property is typically applied with just continuous variables when you're transforming these things? So how does that, I mean, just, and I don't know if I should go into like detail about this, but like, how is that separate than just finding the MLE? Like, how does, I guess I'm just confused as like.
Yeah, no. So basically, say you have like the theta hat MLE for the Poisson is y bar, right?
Yeah.
And you want to know, okay, so what's the MLE for theta squared? And we know the MLE for theta squared is going to be theta hat squared, which is equal to y bar squared. However, and we know this to be true because of the invariance property. Sorry, I'm watching a dog and he's.
That's okay.
Getting pretty excited. Hold on, I'm just gonna close my door. So we know that y bar squared is the MLE of this transformation. I'm going to call it like tau of lambda equals lambda squared. So that's the transformation is lambda squared. And we know that.
Right. Okay.
That's the MLE because of the invariance property. But in order to get any kind of confidence interval around this estimator, we need to have a variance for it.
Yeah.
And we don't know the variance. Like we can't say that we can't use the invariance
Right.
property to find the, I know it's like confusing because it has an invariance in the title, but you can't use the invariance property to find the variance of the estimator. You can just use it to find the MLE of the transformation of the original MLE.
Okay.
So it's like you have a transformation of the original variable. So if you want the MLE of that, you use the invariance property. This is your like informal flow chart. But if you want the variance of that estimator, you have to use the delta method.
Okay. Okay.
And I have to, in some cases, you can sort of actually calculate that by hand, but a lot of the time that's going to be like a really complicated calculation that you don't really want to do. So the delta method
Right.
gives you a way of doing it, giving you at least an approximate variance for that estimator that is like a little bit easier to compute.
Okay.
But, and you
Got
sort of implicitly said that it requires it to be continuous. And yeah, that's true. You have to be able to take a derivative of it. So it has to be a differentiable function, which means it's continuous, or at least continuous at the points where you need to take a derivative.
Okay.
Can I,
Thank you. That explains that a lot better.
Julie, can I try to summarize that?
Sure.
Yeah, so essentially so like this homework assignment started with a continuous outcome. And so we wanted to, like, of course, we on question number 2, we're changing that continuous outcome to be binary, right? And so the invariance property, the MLE, says that we can go ahead and take the estimator, and that still hold true even when we have changed from continuous to binary. Is that correct?
Yeah, so it's saying that we have our original data y, and y has a distribution with parameter lambda, and we can calculate the we can calculate sort of the MLE for lambda, and then since z is a transformation of y, we also can get the distribution of z in terms of lambda. So if we know the distribution of z in terms of lambda, then we also know the MLE of that transformation of lambda.
Okay. But now the problem is not being able to really say anything about the variance of this new estimator, or I guess the transform estimator, and using the delta method to go ahead and get that variance.
Yeah, exactly. So like, and so it's pretty common for us to want to have variances estimators, and like beta hat is the most common example. We want the variance of beta hat so that we can get confidence intervals and compute p-values. And this is the same thing. If we have some transformation of lambda, I like g of lambda or tau of lambda for a general function, in order to get the variance of that transformation so that we can compute p-values and confidence intervals. The delta method is one sort of approach you can take to do that.
Okay. Yeah, I'm just also thinking about 1D, about trying to come up with an easier method for finding the MLE of this problem. I guess I don't understand why wouldn't we just be able to use the invariance property of MLE to find the MLE of the transformed lambda?
You mean for which problem?
2D.
Uh, 2D, you said?
Yeah, 2D.
Or do you mean 2E? Potentially.
Well, because A and B is asking us to find the MLE of this lambda once the data has been transformed to binary.
Mhm.
And then D is asking what would have been what would have been the alternative way of finding that MLE of lambda.
Why are you assuming you can't use the invariance property there?
I guess I'm assuming that you can use the invariance property of the MLE to go ahead and find it without having to like completely recalculate it. That's what I'm thinking.
Yeah, definitely. That's
Okay.
That's good thinking.
Okay.
Office hours are done now, but I'll stand for another couple minutes if you guys have any more questions.
I'm still having trouble with 2C and 2D, but I think that's a good explanation. I think I could try to attempt those from here. I think I'm just looking at this more from a big picture standpoint. I'm getting kind of confused with all these different things. So just have to keep trying to attempt it, I guess.
Yeah, if there's like a particular place where you think you're stuck and you want to talk through it, we can do that.
Okay.
Can we talk quickly through, we don't have to be quickly, but turn number 3, like I'm having a hard time wrapping my head around like the sequence, the sequence of these problems, right? So we're first given a continuous output, have to calculate the estimator and do hypothesis testing and so on and so forth. And then number 2 is the same thing, except now where a variable or outcome has been transformed, right? So now we have to think about the invariance property of MLEs. And then 3, like I guess I'm having a I'm sorry, I also missed half the first part of class of office hours today because I had another meeting. So just kind of like at a high level overview of what am I working with now. Now I'm estimating a particular outcome instead of just like an entire data set.
No, it's just a different estimator for something else you might be interested in your data. So when they say like an estimator for the proportion of zeros, they're just like, that might be some piece of information you're potentially interested in, and this is one estimator for it. You want to investigate its properties. But I actually walked through that one in part 3A, at least in some detail at the beginning of the office hours. So
yeah, I unfortunately missed it, but I can go back to it today and post a discussion question if I still have some.
Yeah, and actually I recorded that piece, so I would just I'm gonna upload this after class, so I would encourage you to take a look at it.
Okay, sounds good. But now we're having a different estimator, correct?
This is a different estimator than the ones from the previous problems.
Gotcha. Okay, sounds good.
Thank you, Julia.
Yep, you're welcome.
Yep, thank you. We'll see you next week.
All right, bye.